In this video, I'll be covering Chapter 13, AC Fundamentals. Here's a list of the topics that we will be covering in this lecture, and I want you to understand that you must understand these concepts in order to do the math in Chapter 15. Number one, we're going to talk about the power grid. Number two, transformers. Number three, electromagnetic induction, which is a term that you need to remember. Number four, AC generation. Number five, the 360-degree sine wave. Number six, the oscilloscope. Number seven, waveform magnitude. Number eight, waveform frequency. Number 9, 120 volts, 60 hertz. Number 10, direction of current flow. The power grid. Alternating current is used throughout the power grid. It's important that you understand that when we're talking about the power that is coming from the power plant, being generated in the power plant, and sent throughout the power grid, as you see pictured here, is alternating current. Starting at the power plant where it's generated, then it's transmitted and distributed to various industrial, commercial, and residential customers. So why do we use alternating current in the power grid? One of the major reasons why is because of the transformer. And this is why AC won out over DC. By use of the transformer, we can step up or step down voltage at the point of use with a transformer. But the thing is, transformers only work with AC. A transformer will not work with DC. So, for example, the typical voltage that is distributed out through the residential network, the voltage that's coming down your street at the top of the utility pole is about 7,600 volts. And of course, as we've all seen all of our life, the pole-mounted transformer that is in between the high voltage coming in of 7,600 volts will step that voltage down to two legs. It's not two phases, but it's two legs of 120 volts. So in our homes, coming out of every one of our residential plugs, receptacles, is 120 volts. Now there's some exceptions for hot water heater, for our ovens, for a central heating unit. Certain devices in our homes do use 240, but what this is not two phases, but two legs of 120. So the reason why we use AC voltage instead of DC voltage throughout the power grid is because of the transformer. The transformer is one of the primary reasons why AC is transmitted and distributed throughout the power grid, so that the voltage can be stepped up or stepped down at the point of use. If we wanted to use DC instead of AC, you would have to have a set of wires coming straight from the power plant all the way to your house carrying 12 volts. You'd have to have another set of wires coming all the way from the power plant to your house carrying 24 volts, and another set with 60 volts, and another set with 120 volts, and another set with 240 volts. It's just impractical. Where with AC, we can just send one voltage and we can step it up or step it down to whatever level we need it to be once we reach the point of use. The definition of alternating current, and you need to write this down, pause the video and write this down. The definition of alternating current is an electrical current that continuously varies in magnitude and periodically reverses in direction. And we're going to take a close look at that here on our next few slides. So it continuously varies in magnitude and periodically reverses in direction. So where does this AC voltage come from? And a more precise way of saying that is, how is AC voltage generated? Now, if you remember back to the Chapter 1 lecture in INST 1111, when we first got started, we talked about a lemon battery. And a lemon battery, basically you take two different kinds of metal, two dissimilar kinds of metal, you put them in an acidic compound, and it will generate, by means of something called chemical action, a DC voltage. So it's very important for you to understand that batteries use chemical action, and chemical action always generates a DC voltage. But what about our AC voltage? Well, a very important concept for you to understand, and as I said, a term that you need to remember, is electromagnetic induction. Now, this word is actually spelled with a little m here, electromagnetic induction, like that. But I like to put the big M to show you that there are two words contained in one here. The first one is electro, and the second one is magnetic. So we've got two words put together here, electro and magnetic. And basically, magnetism and electricity are two different sides of the same coin. We can create magnets with electricity. Anytime electrical current goes through a wire, there will be a magnetic field around that wire. So we can create magnets with electricity, kind of like what you see at the salvage yard, where they pick up all of the scrap metal and move it with the big circular disc hooked up to a crane. You pick up all the scrap metal and you move it, and they move it and they let go of it. Then they go back to the pile, they pick up another load, and they move it and they let go of it. Well, basically all they're doing here is turning on and off some electrical current through a spool of wire that is inside of that big disc, and that allows them to move that metal by creating an electromagnet. On the other side of that coin, we can create electricity with magnets. So if you look on the screen here, this is my magnet with our north and south pole, and we know with magnets opposite attract, and we've all felt that magnetic attraction between two magnets. And there's lines of what is called magnetic flux going between the two magnets, causing there to be a magnetic field between those two magnets. That's what causes them to be attracted to one another. If we take a wire and we move it through this magnetic field, as we're moving it through this magnetic field, it will create inside of that wire an electrical current. This is called, or this is done by means of electromagnetic induction. In order to understand why an electrical current is created in this wire as we move it through this magnetic field, we have to go back to the molecular structure of the atom. Now, I want to point out to you here that it is very important that you understand that you cannot take the wire and just put it in the magnetic field, leave it there, and it will create electricity in the wire. No, you must be cutting across the magnetic field. We have to be moving through the magnetic field in order to induce in the wire an electrical current. If we just take the wire, set it there, and leave it sitting there still, it will not create a magnetic field in the wire. It will not create in the wire an electrical current as long as it's stationary. So if we go back to the molecular structure of the atom, we understand that the nucleus of the atom is made up of the proton and the neutron. And orbiting around that atom, like the Earth orbits around the sun, is the electrons. Now, whenever we have a material, an element like copper, that has a very few number of electrons in its outermost shell, it is what's called a conductor. So if we move a conductive wire through this magnetic field, what happens is it would be as if God came across our solar system with a giant magnet, and the force of that magnet was greater than the Earth's magnetic attraction to the sun, and the Earth would just go propelled through space. So that's what happens when we move this conductor through the magnetic field. It causes the electrons to be moved away from the nucleus of the atom and to move from one atom to the next, and this is electrical current flow. So it's all about the magnetism. So we're introducing this conductor into a greater magnetic field and therefore causing the electrons to be moved. So as this wire is moved through this magnetic field, we're going to create an AC voltage. Remember, chemical action is going to create DC. Electromagnetic induction is going to create AC. And it's going to create something called a sine wave. So let's look at our sine wave here. And you'll notice that when we first get started, our conductor here, he's totally out of the magnetic field. He's not cutting any lines of magnetic attraction. So at that point, the waveform is at 0 volts. As we move the wire and we begin to cut some of the lines of magnetic attraction, the sine wave will gain. It will produce more and more voltage until we get in the middle of the lines of magnetic attraction, and at that point, we're cutting the maximum number of magnetic field lines, and we're going to reach our maximum positive voltage. Now, as we continue to move, we begin to move out of the magnetic field, and as we move out of the magnetic field, we begin to produce less and less voltage. So we collapse back down again to the 0 volt axis. So we're totally out of the magnetic field. Now we're going to reverse and we're going to come back through the magnetic field again, and we begin to come back down and we begin to cut a few lines of magnetic attraction until we get into the middle of the lines of magnetic attraction, and at that point we're producing the maximum amount of voltage because we're cutting the maximum number of magnetic field lines. As we keep going, we move completely out of the magnetic field. Once we move completely out of the magnetic field, we collapse back down to 0 again. And this wave just continues to happen as our conductor is moved through the magnetic field. Now, a more appropriate way to represent this and how it's actually done in real life, if we look here at a simplified AC generator, instead of having a wire that moves up, completely comes to a stop, moves down, completely comes to a stop, you can imagine that would be pretty rough on your machine, tear your machine up after a little while. What is done in actuality is a wire is rotated inside of a magnetic field. This wire's rotation inside this magnetic field will generate an AC voltage, and it will go through a full 360 degrees of rotation. And we're going to look closely at that 360 degrees of rotation here in a second. Understanding the 360 degrees of rotation is important for you to be able to do the math in Chapter 15. Again, if we watch the wires here, you see that we're cutting a maximum number, then we move out, then we come back through, we cut a maximum number again. And the speed at which this coil of wire here turns determines the frequency of our AC signal. Alright, so here is some very important waveform details, and you're probably going to need to pause. After I describe a few things to you, pause the video and write a few things down. All of what I'm going to show you here on this sheet is going to tie into the formulas we'll be using in Chapter 15. So we begin here at our 0 volt axis. So this line right here represents our 0 volt axis. Our sine wave is going to begin at the 0 volt axis. As the wire is cutting through the lines of magnetic attraction, we will reach our max positive at 90 degrees. You need to write that down. We reach the max positive at 90 degrees. We'll continue to rotate. We come back to the 0 volt axis. As we continue to rotate, we come down here to our maximum negative. That happens at 270 degrees. So we have a max positive at 90, a max negative at 270. As we continue to rotate, we'll complete our full rotation of 360 degrees. We're going to cross the 0 volt axis 3 times. You need to write this down. We're going to cross the 0 volt axis 3 times at 0 degrees, 180 degrees, and 360 degrees. Those 3 degrees we will cross the 0 volt axis. Again, we reach our max positive at 90 degrees, we reach our max negative at 90 degrees. 270 degrees. Max positive at 90, max negative at 270. And there's one other degree rotation that is very important to us, and it's called RMS. RMS, as you see here, is the equivalent DC value. The equivalent DC value. That occurs at 70.7 degrees, and we'll be doing calculations to find RMS and to convert from RMS to find what is called peak. So if we look over our waveform some more here, you'll notice in yellow from the 0 volt axis to this peak right here, we call that voltage peak from here to here. From the top of this waveform to the bottom of this waveform, we call that voltage peak to peak. From the bottom to the very top, voltage peak to peak. And here's our voltage RMS. And voltage RMS is the equivalent DC value. So let's say we had a situation where we had a camp out on the lake, and we had an electric stove in there, and we had been running that electric stove on batteries. And we had always run it at 120 volts DC. But finally they run high power wires they run AC voltage to our camp. And now we want to heat that oven up to the same temperature that we were getting before. Well, in order to heat that oven up to the same temperature we were using before, we can't just have 120 volts AC, but in order to get the equivalent of 120 volts DC, we've got to bump it up higher, because if you look at your AC sine wave, we're not always getting 100% output. So if we look at our sine wave, all in this area, we're losing power. In this area, we're losing power. So in order to get the equivalent DC value, we have to go up to what's called peak. So in this case, in order to get 120 volts of AC power, 120 volts of DC power, we would have to actually go up to 170 volts. And all that will become clear to you when we do the math in Chapter 15. These waveforms that we're looking at here, those waveforms are displayed on a piece of test equipment called an oscilloscope. And what an oscilloscope does is it'll actually show you the waveforms instead of what a DMM, a digital multimeter just shows you a number. But an oscilloscope will actually show you the waveform itself. So it's important to know what an oscilloscope is and what it's used for. It's an electronic test equipment used to display and analyze electrical waveforms and signals. So here on the right we see our digital multimeter, and as I said, it only shows a numerical value. It will not show the waveform. And I want you to know, it's important for you to know that DMMs always show RMS. They always show the RMS value. If you look at a meter at the top, it will say true RMS multimeter. So when we look back at our waveform here, we got all these different values we possibly could be talking about, whether it be voltage RMS, voltage peak to peak, or average voltage. What the meter always shows is RMS, the equivalent DC value. If we were to compare what a DC voltage signal would look like to an AC voltage signal on an oscilloscope's display, what a DC voltage looked like would just be a constant straight line. If we turned off our DC voltage, it would just go down to the 0 volt axis and it would just show you 0. Whereas an AC voltage is going to go from its 0 volt axis to max positive, back down to 0 volt axis, max negative, and so forth. Now in our definition of an AC voltage, we said it's one that continuously varies in magnitude. Well, let's talk about that magnitude a little bit. And basically what magnitude is, it determines and it displays your voltage level. And the magnitude is from the top of your max positive to the bottom of your max negative. The greater the size of the waveform, or as we say magnitude, the greater the magnitude of the waveform, the more voltage. So here we have the same frequency but less voltage. We've gone from a certain voltage here and we've reduced that voltage here, but you can see the waveform is basically the same frequency. We can vary this magnitude of the waveform with our generator by increasing or decreasing our magnetic field, or the amount of wire that we send through the magnetic field. We can vary the amount of our voltage. Frequency is another term that you need to be very familiar with. Frequency is measured in hertz. So here at the top we have a high frequency signal. At the bottom we have a low frequency signal. You can see that in the time that it takes this waveform here to go through one cycle, that this waveform here has already went through many cycles. So the amount of waves in a given period of time is its frequency. This frequency comes from the speed at which the generator spins. Here's an example of a lab being done where the frequency is being increased. This piece of test equipment over here is called an audio signal generator, and basically what he's doing is he's increasing the frequency of the signal, the audio signal being fed into the oscilloscope. So you can see that the waves get tighter and tighter together, and there's more waves displayed in the same amount of space as he turns up the frequency. In this picture here we see the same frequency, but if we were to use a variable voltage supply, Here we're increasing voltage, and it increases the magnitude from the top to the bottom. It increases the magnitude of our wave when we increase our amount of voltage that we're producing. The frequency stays the same amount of waveforms, but the height and the depth of the waves is magnitude, and that tells us how much voltage. I definitely want you to memorize this. You will see it on a test. The standard voltage in the USA coming out of the wall is 120 volts, 60 hertz. That's something that you just need to know in life, period. But it's definitely something I will be putting on test that you will see in the future. The standard voltage in the United States coming out of the wall is 120 volts, 60 hertz. Yeah, I know it's 240 on the oven and different places, but we're just going to go with our standard receptacle, 120 volts. Our frequency is 60 hertz. Why 60 hertz? Well, guess what? Anything you want to know more about in this lecture, you can YouTube your question and you'll find hundreds of videos to discuss what you're looking for. Okay, another part of our definition, we said it periodically reverses in direction. Periodically reverses in direction. So on the left here we see a DC current. And we can see our electrons are moving in one direction. And let's say this is a light bulb here. As long as the electrons are moving through the light bulb is going to get hot due to friction. It's going to heat up enough to glow and light up the whole room. On the right over here, we see alternating current. So the electrons go this way for a while, then they go this way for a while, then they go this way for a while, then they go this way for a while. Guess what? The light bulb does not care, or if you're looking at the heating element on the stove, it doesn't care which way or if the electrons are moving back and forth. It doesn't care. As long as the electrons move, that's all that matters. If the electrons move, then that heating element's going to get hot. That light bulb is going to light up. Okay. Next up is going to be Chapter 15, Resistive AC Circuits. We can tell that it's AC by the AC power source symbol. Here tells us it's AC. We can see our resistors here. We're going to use these formulas. You will be allowed to use this formula sheet on the Chapter 15 test. And we're going to be doing our series, parallel, and combination. But instead of DC like we did before, this time we're going to be doing AC.